photoelectric effect is something that shows up a lot on exams. And the good news is it's not actually that hard. I like this joke here from Science Cat here. A photon checks into a hotel and is asked if he needs any help with his luggage. No thanks, I'm traveling light. Ha. So let's talk about photons themselves. So what they are, they're little pieces of light, right? It's a little sort of particle of light. And if you have a photon, it's incident on a metal surface. So for example, it could be something like zinc. So let's say here we have a little metal here. And what I'm going to do is have a photon coming in. I'm going to use a proper sort of Feynman diagram notation, use a squiggly line here. Here's your photon coming in. Now, it's going to come into this zinc here, and under certain conditions, which we're going to talk about, you could have electrons ejected. This is what happens here. They're emitted. We call them photoelectrons for a reason, right? Because they're electrons that came from photons. So photons caused electrons to come out. That's why I like the term photoelectric effect. The definition is in the name. Photo means light, electric means electron. So you have a photoelectron. That's how you know it's light and electricity. Now there's features of it. So this is what's really interesting about it. Because how's this? I'll show you this. Remember this equation, E equals HF. That the energy of light, for example, should be dependent on the frequency. So it made sense to a lot of people at the time, this is in the early 1900s, that if you had this effect right here happening, that, you know, these electrons should also be given that energy. In other words, if you had a photon coming in with a certain energy, E equals HF, it should make sense then that those electrons would have that same energy, or at least very similar. Certainly it should go in the same way. They fully expected this graph to be linear. They expect it to do something like this. In other words, you know, at no frequency, well, then there's no energy, so then there should be no energy out. And at larger frequencies, it should have larger energies of electrons, because it was able to impart its energy to those electrons. The problem is, this is not what happens. What really happens is this is what really confused people. There exists a threshold frequency below which nothing will happen. In other words, no electrons will be emitted. So maybe it goes something like that, let's just say. So then this right here would be this magical value here. This frequency here, there's some value right here. We're going to call it F0. That's called the threshold frequency. What's really weird is this. Remember, it depends on the energy of your photons. So if you have photons with less energy than that, so in other words, different colored photons, remember, less energy means less frequency. That means greater wavelength. So if you have photons with a greater wavelength, they have less energy. And at some point, you get to where nothing happens. No photoelectric effect happens. And this was absolutely confusing. Because why should there be this threshold? I mean, shouldn't it just be linear right through the origin? And keep in mind this, increasing the intensity of the light, that has no effect on the kinetic energy of the electrons. The only thing that changes the energy of the electrons is this: once you pass this magical threshold frequency, once your photons have more than this amount of magical energy here, E equals HF0, then you always get this photoelectric effect happening for larger and larger frequencies. And then it works linear. Then it goes how it should. It's just this weird thing, like, why is this here? Now above this or here, like I said, the electrons, the kinetic energy of the electrons is proportional to the frequency, right? So you have this, right? Yeah, E equals HF. So it's some sort of graph, and you could take the slope of this, and you'd end up probably with something relating to H. So this is how it goes, but this is really confusing. So along came a really clever guy by the name of Einstein. I'm sure you've heard of him. And he figured out the reason, among other things. He figured out, well, first of all, the energy of light is quantized. That means photons have energy that's a multiple of H. That's why we have that equation, E equals HF. Now we have electrons. This is his idea, was that the electrons must be trapped in the metal. And they're being held, they're being bound in the metal by some sort of energy. We call that energy the work function. And that's going to be measured in electron volts usually. It could be in joules. But basically it's the energy needed to eject the electrons. So if you think about it, you've got these photons coming in with a certain energy, E equals HF. But if they don't have enough energy to overcome this work function, in other words, if they come in too low energy, like, like over here on this graph, like over here, those photons don't have enough energy to overcome this work function. And what is this work function? It's like this amount of energy that's holding those electrons in. So you have to have enough energy to basically force them to be released. So that's the brilliant thinking of it. He actually won the Nobel Prize for this. So what I think is interesting is if the energy of the incoming photons is less than this phi here, this work function, it's not enough energy to eject the electrons or overcome the work function. So that's why no photoelectrons are seen. That explains the threshold frequency. And then you're given this really handy equation here. Emax equals HF minus phi. Keep in mind the units here. Look, this right here, isn't that an energy which could be measured in electron volts? We have HF. Isn't that the energy of a photon? So yeah, so that's an energy measured in electron volts. And then we have this weird work function thing, but that's an energy measured in electron volts. So we have like energy equals energy minus energy. I hope that makes some sense here. So the interesting thing is this Emax, what is that? It's the maximum kinetic energy of these electrons. So these electrons that are shooting out of there, that's their maximum kinetic energy. You can use that to find their speed, I guess. H is still a constant. Remember, it's 6.63 times 10 to the minus 34. You can look it up. F0 is your frequency of the incoming light. So this HF could also be equal to HF0. That could be actually it. So let me actually just delete this one here. It doesn't have to be it doesn't have to be F0. It could just be F. So that's the frequency of the incoming light. So remember, in this E here, that's the energy of the photons coming in. This is the work function, and this is the maximum kinetic energy of the electrons. So it's all written in energies. So now we have an example for you. We have photons, and they have an energy of 2.2 eV each. So each photon has that energy. So they're incident on a metal surface. And first of all, let's find the... Oh God, what have I done? Oh no. Undo. There we go. I think I was under the delete button there. So we want to calculate the frequency of this radiation. So what do we remember that? We want the frequency of these photons. Well, these photons have an energy 2.2 eV. We probably need that. Well, in order to do frequency, we're going to use the equation E equals HF. Does that make sense? We're going to do then F equals E over H. And we know H. H is 6.63 times 10 to the minus 34. You can look that up. But I need to know, what is the energy? I need this in joules. So what I'm going to do is I'm going to have to convert this energy. So 2.2 EV. I have to convert that to joules. And remember, we can do this little fraction trick here. I need something with EVs on the bottom in order to cancel out those top EVs. And then I know that there's 1.6 times 10 to the minus 19 coulombs. Not coulombs, sorry. Joules. In an EV. Remember again where that came from? That came because you know that 1 EV is 1 charge of an electron times 1 volt, and charge of an electron is 1.6 times 10 to the minus 19 coulombs, but coulomb times a volt turns out is a joule. So here we go, we get this. Let's actually figure that out. I guess that would help, huh? So 2.2 times 1.6 times 10 to the minus 19. That gives me a value of 3.52 times 10 to the minus 19 joules. Now I'm going to put that here then. So 3.52 times 10 to the minus 19 joules. Take that answer. Let me just make sure I did it right. Yeah. I'm going to take that answer and divide that by 6.63 times 10 to the minus 34. I should get a lot of numbers here. Oops. Yep. So I end up with the frequency is and I'm allowed two significant figures, so 5.3 times 10 to the 14 hertz. Oops, that's not a hertz. That's a hertz. So there's your answer. That's a very high frequency, isn't it? It's a very large frequency. Now, let's do this one. Assuming the incoming photons have the same energy as above, so in other words, we're going to assume these photons have the same energy, which could be 2.2 EV, or if we feel like it, we could say 3.52 times 10 to the minus 19 joules. Either of these numbers will be the same. That'll be fine. Find the maximum speed of these emitted photoelectrons. And we're this time considering what's a surface of potassium, which is element number, what is that? Well, the element symbol is K, isn't it? But potassium. Now we're told the work function is this. So this is the important part. We know the work function is 1.5 EV. What do I do? Luckily, I have an easy equation. It's actually really easy. Look, Emax is equal to HF minus phi. So let me just write that down. So that way if I'm showing this to my examiner, I can show them I know what I'm doing. So Emax equals HF minus phi. All right. Do I know HF? Do I know the energy of my photons in electron volts? May as well do it all in electron volts. Look. we can say the Emax is going to be in electron volts. I can say HF, but in this case, HF, I can just say that's just 2.2 eV. That's our incoming photon energy in electron volts. The reason I'm doing that is because we're given the work function in electron volts, right? So we have this. This is our Emax. So what's that? That's 0.7, isn't it? So I have my delta Emax, I guess. Oh, I don't need a delta, actually. We'll just say so. My maximum kinetic energy, Emax, is just 2.2 minus 1.5, which is 0.7 eV. And what do I do with that number? I probably need that. If I want to know the speed, do you see that I need to know that EK is half mv squared? So I'm going to need to know everything in sort of proper units. I don't need these electron volts here. So I'm going to try to get rid of the electron volts by, again, multiplying by 1.6 times 10 to the minus 19, because there's that many joules in one electron volt. The electron volts cancel out. I end up with 0.7 times 1.6 times 10 to the minus 19. And this is my answer here in joules. So it's 1.12 times 10 to the minus 19 joules. And now, of course, what do I use that for? Well, I know that 12 times 10 to the minus 19, that equals, because that's a kinetic energy. So that means I know that's equal to half mv squared. Therefore, v equals, let's see, it would be 2 times this. 2 times 10 to the minus 19. It'll be 2 times that, yeah. Divide that by the mass of an electron. What's that? Is that 9.1? Let me just look it up here. What's the mass of an electron? I think it's 9.1. Yeah. 9.11 times 10 to the minus 31 kilograms. And I'll take the square root of all of that. Let's do that on the calculator then. Let's figure that out. So 1.12 times 10 to the minus 19 times 2. Divide that by the mass of an electron. Let's hope we get this right here. At least we've done it right. So then I have this value right here. I have a V then, which is 4.9 times 10 to the power of 1, 2, 3, 4, 5. 4.9 times 10 to the 5 meters per second. Pretty fast. Remember, something like 10 to the 8, that's the speed of light. So these are electrons that are actually going pretty darn fast here. You can see how we can actually solve all this. So photoelectric effect does not have to be so bad. It does not have to be so scary for you.